Hello, my name is Escandor. I am here today with Sancho. For today's video quiz presentation, we will discuss aircraft stall. In order to fly, the cross-section of an aircraft's wings must pitch up relative to the direction of the wind. The pitching up motion of the airfoil typically generates lift. The greater the angle, the greater the amount of lift produced. This holds true only for a range of pitching degrees. Once an airfoil exceeds such a value, it passes the amount of maximum lift it is able to produce and eventually begins to drop. This is normally what we call a stall, and this happens when there is a sudden reduction of lift from the wings of an aircraft. A stall begins to occur when smooth flow detaches over the top surface of an airfoil and turns into turbulent flow. This increases the drag instead of lift because of the separation of air. Even at a low angle of incidence, a stall might still take place. Contamination of the smooth surface of the airfoil, such as frozen deposits and other hardened materials, may reduce the effective maximum angle of attack and introduce stall at an earlier period.
Stall recognition. A full stall is usually involved in an inadvertent loss of control of the aircraft. So it is imperative for the pilot to recognize flight conditions earlier that are conducive to stalls and know how to apply corrective actions in order to prevent it from persisting. There are certain aircrafts that are installed with stall warning devices that identify impending stall. These devices may include an aural alert, stick shaker, or lights, which alert the pilot when approaching the critical angle of attack. Those without any devices installed, pilots rely on sensory cues, which include feel, vision, hearing, and kinesthesia. When feeling, the pilot will feel control pressure change as the speed reduces. Consequently, the pilot must use larger control movements to get the desired airplane response. Furthermore, the aircraft's reaction time to control movement will also increase. From feeling, symptoms before stall occurs can be gathered that may include buffeting, uncommanded rolling, or vibrations. Vision is about maintaining pitch awareness. Hearing is noticing the change in sound made by the air flowing along the airplane structure as speed decreases. And kinesthesia, also referred to as the seat of the pants sensations, is the physical sensation of changes in direction of speed. Stall recovery. The most important action for stall recovery is reducing the angle of attack. The following is an example of a stall recovery procedure for light general aviation aircraft, which is adapted from a template developed by major airplane manufacturers. The first step is disconnecting the aircraft from the wing leveler or autopilot. It is essential that stall recovery is done by manual control. This is because autopilot could make automatic adjustments the flight controls that are not appropriate. The next step is pitch nose down. This is to reduce the angle of attack below the critical angle of attack and is applied until impending stall indications are eliminated. In cases where elevator does not provide the needed response, pitch trim may be necessary. The third step is to bank wings level. This is to orient the lift vector properly for an effective recovery. It is imperative that this is done after reducing the angle of attack, since this helps get the wings flying again. Additionally, the pilot must also proactively yaw while rolling to prevent the aircraft from progressing into a spin. The fourth step is adding thrust or power as needed. It essentially does not eliminate a stall, but this is done to reduce loss of altitude during a stall recovery. The fifth step is retracting speed brakes or spoilers, that is, if they are equipped. This will improve the lift and the stall margin. Last and the final step is returning the aircraft to the desired flight path. Flight control movements should be done smoothly in order to avoid a secondary stall. Now, there are also principal maneuvers to practice stall recovery, but essentially follows the template discussed. First is the power-off stalls, which are simulated to practice the stall under low-powered conditions such as during a normal approach to landing. Next is the power-on stalls, which is a stall under high-powered conditions, such as during a normal approach to takeoff. Then the elevator stalls, which demonstrate the effects of not maintaining a positive airplane control during a go-around or rejected landing. Next is the accelerated stall, which demonstrates the effect of aggressive maneuvering by turning or by making abrupt control inputs. And lastly, as said before, secondary stall, which demonstrates the effect of aggressive recoveries from a preceding stall.
A superstall is a particular kind of stall characterized by substantial loss of control over the tail end section of the aircraft. Elevators of a T-tail empennage are highly susceptible to superstalls primarily because smooth flow gets blocked by the wings as an aircraft pitches at an altitude. Smooth flow transitions into turbulent ones right before reaching the surface of the tailplane, rendering elevator authority useless and recovery measures ineffective. Several fuselage designs have been incorporated to help combat deep stalling on steep climbs. An appendage of the vertical fin that extends below the fuselage, called the ventral fin, is a device that increases directional stability. Good directional stability at increasing Mach number generally delays the onset effects of deep stall at constant angle of attack and helps with the recovery of an aircraft should one might occur. A G-stall is another type of stall where the apparent weight of an aircraft exceeds the amount of lift its wings are able to produce. This usually happens when an aircraft turns a bank from a level flight. This means the force component of lift is reduced. In order to maintain lift, the angle of attack must increase. The amount of lift in proportion to the weight of an aircraft is called the load factor, and its job is to determine the maximum threshold an aircraft may experience before its lift can no longer be able to overcome the amount of apparent weight due to the centrifugal force acting from the turning center. The unavailability of lift due to excessive loading is exactly what a G-stall is, and is typically often experienced by fast-moving aircraft such as fighter jets and aerobatic planes.
Shock stall, also called high-speed buffet. Shock stall is the sudden reduction of lift and increase in drag due to the airflow separation caused by shock wave. This phenomenon is brought about at high Mach numbers, usually when the aircraft is flying above its critical Mach number. And as the aircraft increases its speed, the shock waves will also grow larger. This causes the sudden separation of the airflow, which in turn causes the reduction of lift and increase in drag. So in conclusion, not only is buffet caused by reaching the critical angle of attack, but also by flying too fast. That will be all for our video quiz about stalls. Thank you for listening.